Hello, and welcome to your first video introducing the idea of plastic analysis. To introduce the idea, let's remind ourselves of the mild steel stress-strain diagram. The stress-strain diagram that actually has that short little perfectly plastics section where we just gain strain without any additional load, and then of course we move into strain hardening. Now on this plot, we can see we have the yield stress and the yield strain, and they basically occur at the end of our linear region. And then we also have an ultimate stress that continues on after we get into strain hardening. Now, when we start getting into plastic behavior, we want to look at what our actual stress distributions might look like on a section. And so I've drawn some different members here. I've gone ahead and broken them just so to show that they're longer than this short little stubby sections I have, but they wouldn't fit on the page. And so on the left, we have axially loaded member, and I'm saying that the P that's applied is greater than a P that would cause the material to yield. So the axial force is that large, and the beam on the right has pure bending, moments equal and opposite on both sides, and that moment is greater than a moment necessary to cause the material to yield. And if we look at how the stress distributes, when we think about axial loading, we know that where P is applied can cause local deformations. And so if we get that local plastic deformation, if we're too close to the support and not further back in where the load has distributed out, we're going to get this parabolic distribution instead of our nice linear distribution that we're used to seeing. And we're going to say that that's just our axial stress that's now acting. When we think about the bending stress that comes from our moment, what we actually see is when we start yielding plastically, that we stop having a linear relationship and we're going to see a parabolic relationship. Remember, when we found our equation for bending stress, our MC over I, we had assumed the behavior was linearly elastic, and of course it no longer is, and those equations sort of fall apart and aren't valid anymore. Further, it's important to note that with plastic behavior, the yielding doesn't necessarily occur simultaneously through the whole cross-section at the same time. So you'll have some materials that are still behaving, some portion of the material that's still behaving elastically, and then other portions that are now behaving plastically. Now, the actual plastic analysis methods, like true plastic analysis, that is a high-level graduate course. So it's definitely beyond the scope of where we're at now. So instead, we want to introduce some elasto-plasto methods or elastic plastic methods and the behavior of what that looks like. And there's two things that we're going to look at. First, a perfectly plastic and then a bilinear. So if we approximate our plasticity, we want to start with the mild steel Elasto-Plastic method, and what would happen is that we ignore strain hardening. We say that we either are below yield and below the yield strain, or once we hit yield, we are perfectly plastic. And of course, we have our modulus of elasticity that we would initially load along that slope. But once we hit yield, we just keep deforming without any additional load until we choose to take the load off. And of course, when we unload, we would unload with the same modulus of elasticity slope E. The amount of recovery, since we're not unloading straight down, but we unload with that recovery, that's going to be the same amount of elastic strain that we had at the beginning. That's our elastic snapback, if you will. And that's all recovered strain. So the permanent strain that we're left with is going to be the distance from the zero strain where we started out to where we unload to. And that's going to be our permanent set, or the amount of deformation and strain that we don't get back. Now, one of the key things to note on this drawing is that sigma never exceeds sigma yield. This is critical to how to solve these problems, and this will be tricky for some of you to remember this and use this as a tool, but this is just a tool now in your tool belt. If you have a problem where you're told a member has yielded, then you immediately know the stress in that member because it's your yield stress. So remember that. Now, sometimes this is not a good enough approximation and we want to go a little bit more refined, and so we'll estimate materials as bilinear. And so what that means is we want to try to capture a little bit of that strain hardening behavior, but we do it with a straight line. So we have two straight lines that break at the yield stress. And so at our yield stress, we're still going to have our yield strain. We're still going to have the modulus of elasticity, that is the slope in the elastic portion. And then when we start loading up the second curve, then we have to add more load. And when we unload, we're still going to unload on the slope E. That hasn't changed. Now, fortunately, a ton of research has already been done, and so these curves will be given to you. You don't have to make them up. So you're going to know what your sigma yield is, you're going to know what your sigma ultimate is, and you might be told you're going to be loading to some other value sigma that's in between those two values. So you can actually use the slope of the secondary curve with the stress that you're at a certain point to just then pick the E value that you're at when you start to unload. And so then you can determine your elastic recovery, at which point you can also then determine your permanent set. So that just becomes some geometry and trig, and that's all that's happening there. Now, before we look at an example and watch another video that has an example on how to solve a problem using one of these approximating plasticity stress strain diagrams, let's go back and revisit that stress distribution, because those parabolic stress distributions are stressing me out. Haha. So what we want to look at instead are some idealized stress distributions. We have to assume the material is isotropic. Remember, if it's not isotropic, like steel, same stress capacity in all directions, once we move into plasticity, the centroid necessarily for the neutral axis of our stress and strain does not align with the geometric center anymore. That can vary. So we're going to look at an axial case, and then we want to look at bending. And bending is going to take some different scenarios. So we're going to look at a few there. So when we look at our axial, we're literally just going to be able to assume that it's the same stress distribution that we're used to. P over A, nothing's changed, the stress is constant, and the cool thing is, if we're talking about a mild steel, that elasto-plastic, perfectly flat plastic line, if we're talking about that behavior, well then we know that our stress is always less than sigma yield. So that's great. So axial is pretty straightforward. Now to look at bending, we want to give ourselves a little refresher. So for our bending refresher, we want to remind ourselves that sigma max is always just the applied moment times C over I. So our MC over I. So sigma yield, we could say, occurs at the moment that causes yield times C over I, or more importantly, we could define the moment that would cause us to be at yield is our yield stress times I over C. Because that moment that causes yield is important to us because we want to know when are we going to get into the plastic range. And as an additional reminder, we're going to call this positive bending is the loading we're going to put on this member. So it's going to be smiling. We'll have tension on the bottom, compression on top. Those two moments are equal and opposite. So let's see what it looks like for our first case. So just from our moment up there, we know we'll have compression on top, tension on the bottom. We should have the same stress distribution on both sides of the beam. Those should be equal and opposite. And the maximum stress that we experience at the outer fibers, we're going to say is less than sigma yield for case 1 here. So that means our applied moment is less than the moment that causes yield. Great. Let's look at the next beam. Let's add a little bit more load. So now our stress scenarios are going to get just a little bit longer because we've added a little bit more moment. We still have compression on top, tension on the bottom, and now we're going to say that the maximum stress equals sigma yield. So we've got just enough load on there to yield our outer fibers. So for case 2, we're saying now that the moment applied is the yielding moment. But let's add a little more load. So now we're going to add a moment that's greater than sigma yield, but less than some other moment we're calling the plastic moment, and we'll get to that. Now in this case, because we're now yielding more material, we're going to have to yield more material because we're adding more moment. So that means that the yield depth will increase. It's no longer just the outer fiber. We're starting to yield a little bit into the depth as we approach the centroid. So we're going to have this rectangular yield profile at the top and bottom, and then into our linear as we approach the centroid. And our sigma max, though, cannot exceed sigma yield. And then finally, we're going to set our moment equal to the plastic moment, the highest value. And here, we keep adding moments and we keep making the yield surface deeper and deeper until we've yielded all the way from the outer fiber of bending to the centroid. And so this now is what we call the plastic moment. Now our maximum stress is still sigma yield. We haven't gone any higher than sigma yield. It's just once we yield the outer surface, if we add more moment, then a little bit deeper into the cross section has to take over and handle that, and then it yields. And then if we add more load, a little bit more comes in and we get more yield. And we're going to say that this plastic moment, just so you have the definition of it, that is the moment that causes yielding through the entire cross section. Now, even though this is idealized and there's some approximations going on here, you can get some decent analysis back out of members and sizing. And when those of you who take structural systems, Civil 148, you're going to see that this same basic theory is what is applied to design steel members per the code. And not only would you have a section modulus S, which we know is just I divided by C, but there's now a plastic section modulus as well, Z, that you're going to learn about, that is when you're hitting that plastic zone. Thanks for watching. Your next video is an example of how to solve one of these problems.